I know that you probably don't have any questions. There were only 3, and I think we had lots of time to get yesterday our questions answered about these. But nevertheless, I would like to review this. We're going to step away from inclined planes today and talk about a different type of analysis dealing with forces, and then we're going to go back to inclined planes a little bit later. A couple of you had inquired as to when you felt, or when I felt your unit exam would be. It's definitely not next week. It'll most likely be the following week, but I have to take a look at all of the lab activity and stuff we're going to do. I'm guessing '26th, 2 weeks from today kind of thing. Don't forget, this unit is called Dynamics and Gravitation, and all we've been dealing with so far is dynamics. We still have to deal with gravitation, so it's a pretty big unit. Okay, when you have an object on an inclined plane and there is friction, shouldn't matter which way the plane is facing, but most people like to see it this way. So I have now an object that's on that inclined plane, and whatever angle it's at is really not relevant to what I'm about to explain. Forgetting about force of friction for a second, we know that there is a force of gravity acting on this. But since the box cannot move in the direction of that force, and since we normally talk about horizontal and vertical components, when we put that idea together, horizontal and vertical components are useless because the box will not move horizontally or vertically. The box instead, let me show it to you this way. If I take a look at what we normally do for our axes are normally like this. Right? Horizontal and vertical. But since the plane changes the direction the object can move, we have to now talk about this as being a set of axes that we're interested in. We're still looking at components. It's just that it's not a horizontal component. It's a component that's along the ramp or parallel to the ramp. And we will also have a component that is perpendicular to the ramp. So all we're doing is we're twisting our frame of reference. But what you need to know is that this force of gravity, and I can label it, that this force of gravity can be broken into a component that acts against the ramp and a component that acts parallel to the ramp. So that force of gravity is what really is pulling on the box, but we can think of it as doing 2 things. It's pulling the box against the ramp, and that is the perpendicular component of the force of gravity, and it is also pulling the box along the ramp, which is the parallel component of gravity. And I understand when students look at this, it seems weird. It makes more sense if I draw this up here, I think. It's doing 2 things. It's pushing the box against the surface of the ramp, and it's pulling the box along the ramp. When you look now, I'm going to get rid of this. When you look at those 2 forces, there is also another force that acts perpendicular to the surface. Somebody willing to volunteer why this other force has to exactly balance the force of gravity perpendicular? Alex? I would tweak that answer just a little bit and say, because it's not accelerating in that plane. It's not accelerating perpendicular to the ramp. Okay? And this, of course, is called the normal force, which leads us to the point of doing this. And we're going to analyze things in more detail with ramps tomorrow. That this is the normal force, which is needed to calculate the force of friction. When you go to your formula sheet, the force of friction can be found by taking the coefficient of friction multiplied by the normal force. In this case, when you look at this, this is your eyeball. When you study this, you can see right away the normal force is equal but opposite to the force of gravity. So you customize your force of friction formula to be this. I almost made a mistake and forgot the perpendicular. And then you go to the equations that would be provided to you on an exam, which are FG parallel equals FG sine theta. Make sure I got that right. Yep. And FG perpendicular equals FG cos theta. I want to make sure you understand the G's in these formulas are subscripts. They're not 9.81. They're just subscripts. That means I can put over here that the force of friction on an inclined plane is mu times mg cos theta. And that would calculate the force of friction, which is in the opposite direction. And you might get a force of friction greater than the force of gravity parallel. And if you do, it just sits there. But if you get a force of friction, that is smaller than the force of gravity that is parallel to the ramp, then the box is going to accelerate in the direction of that parallel component of gravity. But ultimately, what we were dealing with yesterday are the equations in green and the derivation of how to find the force of friction on an inclined plane or a ramp. So I don't know if you have any questions. Can you take a look at those 3 problems that you were working on yesterday? Any questions? Yeah. 3? Okay, let's take a look at number 3. And I suspect maybe, Jay, the thing that puts you off right away is that 15 Newton object. So let's take a break from that for a second and go back to when we learned about mass and weight a few days ago. There's all kinds of differences. Mass is in kilograms, weight is in newtons. But there's a formula that connects these things together, right? That mass is m, weight is the force due to gravity, and the thing that ties those together is this formula, right? So if you know the weight of an object, you could calculate the mass using this. Okay. Now I'm just going to, for the sake of my explanation here, let's just imagine that G is 10 newtons per kilogram. We know it's 9.81. I just want to use 10. What does that mean? It means that if I had a 1 kilogram puppy, some bulldog puppy, a 1 kilogram puppy, if I multiply that by 10 newtons per kilogram, I'd get the weight. Now, really, again, I'd multiply by 9.81, but I'm using 10 to drive a point home. Then I have a 10 Newton puppy. And when I say a 1 kilogram puppy, I'm telling you the mass of the puppy. And when I say a 10 Newton puppy, I'm telling you the weight of the puppy. And we would make a very important assumption here that I think is obvious. We're not flying the puppy to the moon. Okay? We're talking about on Earth here in Alberta. So what if I had a 12 kilogram baby goat? I don't know. Doesn't matter. A 12 kilogram kid, I guess they're called, baby goat. That would be 120 newtons, wouldn't it? Or 12 times 9.81. And my point is this. Whether I call the puppy a 1 kilogram puppy or a 10 Newton puppy doesn't change the fact that it's that object. And whether I call it a 12 kilogram goat or a 120 Newton goat, whether I talk about its mass or its weight, it's that goat. And for that reason, occasionally you will see something like this, a 15 Newton object. Well, that is a blank kilogram object, right? And if we wanted to, we could work backwards and divide that by 9.81 to get the mass, okay? With all that being said, let's look at solving this problem. What is the force of friction? So you start off with your formula for force of friction. It's mu times the normal force. After a while, I think it's beneficial for everybody not to have to draw the ramp each time, not to have to go through this on paper all the time, but to understand that if you did, the normal force is the perpendicular component of gravity. So for question 3, this becomes force of friction equals mu times the perpendicular component of gravity. Force of friction equals mu times the force of gravity times cosine of theta. Are you still with me? So now we can branch off, because some of you will want to do one thing and others will want to do something different. Some of you will then say the force of friction equals mu mg cos theta. Oh, by the way, I forgot to mention, the theta in these formulas in green is this theta of the ramp. It has to do with similar triangles. We don't need to get into it because you're given the formulas. So, on the other hand, some people will just do the work from here because they will recognize that this is 15 newtons. When we say a 15 Newton object, we're actually told the weight of the object, the force of gravity. So I can just take my mu, which is 0.3, multiply by the weight, multiply by the cos of what I thought I saw was 35 degrees, and get the answer, okay? On the other hand, it's what I'm getting at here is you should always be looking ahead at what you're going to be doing rather than just committing yourself to a whole bunch of work. Because if you blindly say, I'm going to find the mass, because I always need to know the mass, then you would take 15 newtons divided by 9.81 to go to kilograms, and you would get this number of kilograms, but then you would put that number here, where you would then multiply by 9.81. So on the one hand, you're taking 15 divided by 9.81, then you're going to multiply by 9.81, you're back to 15. So if you want to do it this way, you can. If you're confused about the fact that we're going to go back to 15, don't worry about it. Just use this formula, and it will work. Does that answer your question? Okay. Any other questions? All right. We are going to move on today and look at applications of Newton's second law. So this is lesson 20.2.8, and I want you to understand what's going to happen in this lesson. This lesson is like a 4-day lesson. We're going to be looking at many applications of Newton's second law. Newton's second law is what's on the screen right here. I've got it written as it appears on your formula sheet. I've got it written as it would appear on your formula sheet if we didn't care about the directions. And I've got it written in an alternate way. These two statements here are really saying the same thing. They're just saying don't worry about directions. And what we're going to do most of the time, I think, is use this version of Newton's second law. Now listen very carefully. When we analyze problems with Newton's second law of motion, we do not use vectors as positives and negatives. We don't. We don't even use the vectors in the calculations. we use the vector directions to set up the proper formula. Okay? And the proper formula is basically going to almost always be found by looking at two forces competing, and your formula will be the bigger force minus the smaller force equals the net force. So if the bigger force is up and the smaller force is down, you're not going to say this is positive and this is negative. You're simply going to say I'm going to take that number and subtract that number. And that subtraction takes the direction into account. What we are looking at today is vertical motion, specifically vertical motion examples today. Tomorrow, I think we'll look at inclined planes. The next day, we will look at pulleys. There's a lot of variations of applying this. I will tell you right now that if I gave this question to you, many of you would look at this question and feel as though you know exactly how to get the answer, and you would get the wrong answer. And the reason is that you would use F net equals MA, and it would be wrong. You would put 600 newtons for the net force, and you would put 7,500 newtons for the net force, and you would put 600 kilograms for the mass. You will not get the right answer. Can somebody explain why that's not going to work? This is the biggest obstacle we have to get past over the next 3 or 4 days. Jay, do you know? Well, that is true, but since I'm standing in the elevator, what Jay's saying is it's the combined mass, and we're asked for the acceleration of the person. But would you agree that if the elevator accelerates at 4 meters per second squared, if I'm in the elevator, I accelerate at that as well? So it's not to do with the mass. Yeah?
Say, almost like how when you're in a car, it feels like you jet forward when it suddenly stops in a different direction.
Well, that's true, and that actually has something to do with what we call apparent weight. But I don't want to go there. If I told you that I had an object, let's take an object. Give me a second to grab an object. I'm going to grab a 1 kilogram mass. That 1 kilogram mass is like the elevator. And I think you got it, but give me a second here. That 1 kilogram mass is like the elevator. So I have a kilogram mass, and I'm going to apply an upward force on this mass. I am going to, we'll come back to this example in a second. I've got a 1 kilogram mass, and I am going to apply a force upward of 4 newtons. So if you wanted to find the acceleration of this, and you said F equals ma, and you put in 4 newtons equals 1 kilogram times the acceleration, do you agree mathematically that's 0.25 meters per second squared? Okay, so here goes. How many newtons? 4? I'm going to apply an upward force of 4 newtons. Would you agree I'm applying an upward force of 4 newtons? The acceleration is 0. This force, I don't know if you see the mistake I made up here, is the net force in the formula. What am I not taking into account here that is affecting the behavior of this elevator or this mass? The force of gravity. And whenever you use, so I want to spend an inordinate amount of time on this, like a lot of time talking about this right now. Whenever you use F net equals ma, you always have to draw a free body diagram to decide how to find the net force. This is not Science 10 or grade 9 science. This is not because you see newtons, that's the force that goes in the formula. Net force means sum of all the forces on the mass. Incidentally, if you're watching this on video, when I applied that upward force of 4 newtons to the 1 kilogram mass, it didn't even move. There was no acceleration. So what do we do here? Well, we draw the elevator. And it says the cable exerts a force of 7,500 newtons upwards. So one of the forces acting on the elevator is this. It is what we're going to call, what I would like you to call, the applied force. Not the net force, the applied force. Now there is also a force of gravity acting down, isn't there? I'm not so sure I want to draw it yet, because I don't know how long I should draw it. Because if the force of gravity is more than this, then the elevator will accelerate down, which is what elevators do when you go from an upper floor to a lower floor. They apply less force upward than the force of gravity, and gravity wins the battle. So we're going to do a little exploratory calculation here. What is the force due to gravity? The force due to gravity will have a magnitude of m times g, which is 600 kilograms, times 9.81 newtons per kilogram. Again, I want to pause because when you read this question, this looks like a childish question. F equals ma, divide the force by the mass. It is a sophisticated question. It's not a simple question. Was it 600 kilograms? Thank you. So if I take 600 kilograms and I multiply by 9.81, I get 5886 newtons, which is less than the upward applied force. You don't need to get out a ruler and a calculator and work out a scale diagram. Just make sure that it's obvious that downward force is smaller in magnitude than the upward force. So this is 5886 newtons. This is the force due to gravity. So now I want to talk about what I started talking about at the beginning. Nowhere ever do I want to say the force due to gravity is negative 5886. I'm not going to put the negative with the number. What I'm going to do is look at this and say that the net force would have a magnitude equal to the magnitude of the applied force minus the magnitude of the force due to gravity. Those absolute value signs are crucial. Okay, so why am I subtracting the magnitudes of the forces? Because the forces are in opposite directions. And that's how you find a magnitude of a sum. What direction will my net force be in? Well, it will be upwards because the force upward is more. You cannot solve a problem like this unless you see that diagram, either in your head or on paper. It's not just a matter of F equals ma, it's F net equals ma. Then what we would do, just happened there. Then what we would do is you would say ma equals, well, the magnitude of the applied force up minus the magnitude of the force due to gravity. I just made a grievous error in what I wrote. What is the mistake that I made there? It's a horrible mistake. Yeah. Right. I wrote mg. It's not mg, it's ma. It's ma. A is the acceleration. G is 9.81. They're different things. So the bottom line here is now we can put in all of the numbers. We have the 600 kilograms times the acceleration equals the 7,500 newtons upward minus the 5886 newtons that are downward. And I'm not putting a negative there, I'm just subtracting. Yep. Shouldn't the what? So the mass is 600. Oh, I wrote 6. Yours is different. And mine says 75. Yeah, let's go with yours. Otherwise, I think the ride will be a little too wild. Okay, not realistic. I'll have to change mine. I just want to make sure I'm going to change it here. You're saying this number is a 6. Thank you for that. I just want to change it here for next time. That way I don't have the same problem. Okay, so 6,500. Okay, we'll change this. And we'll change this. Okay. Good now? Okay. So we have to subtract these two forces. When you subtract them and you get 614 newtons, that's the net force. That's what equals MA. So you have 600 times the acceleration equals, I think 614, is that right? So we can divide both sides by 600. About 1.02 meters per second squared. Upward. Now, listen carefully. It's not upward because I get a positive answer. It's upward because when I look at the situation, the upward force is greater. Okay. So we get an acceleration of 1.02 meters per second squared. And it's up because the applied force up is more than the force of gravity. Any questions with that first one? All right, number 2. Again, you guys, I'm going to explain this. And remember the word sophistication. We have to answer this in a sophisticated manner. Not like we're in junior high and you're just putting numbers blindly into a formula. That being said, I guarantee you if I gave this as a numerical response on an exam, some of you are going to get it wrong. Because you're going to see a mass and an acceleration, and you're asked to find a force, and you're going to go, well, force equals mass times acceleration. That's the fatal mistake right there. Force is not equal to mass times acceleration. Net force is equal to mass times acceleration. So, how do you decide how to calculate the net force? I know I calculated it as MA, but how do you decide in terms of forces? You draw the situation. And I just don't feel like drawing a rocket. There's the rocket, okay? If I want to accelerate that rocket upward, then I need to apply an upward force, don't I? I call that, we can call it lots of things. Applied, I'm going to call it a thrust force because the engine produces an upward thrust. This thrust force, everybody, is what we're trying to find. It's the applied force. But there is also a force of gravity. Why do I know this is not the situation? And more specifically, it's accelerating upwards. So if it's accelerating upwards, the upwards force must be greater than the downward force to produce a net force upwards. The word net as well as total means what really happens. What's the net result? It goes upwards. So this is the force due to gravity. So when I do this, I say the net force has a magnitude. I'm not going to use the vector symbols and the absolute value signs. I hope you understand when I write F net this way, I mean just the magnitude. Equal to the thrust force magnitude minus the magnitude of the force of gravity. If I say, this is subtle, which means it's slippery to wrap your head around. If I say the net force equals the thrust force minus the force of gravity, that's an incorrect statement. The magnitude of the net force equals the magnitude of the thrust force minus the magnitude of the force due to gravity. So all we're going to do is we're going to put MA here. mg here, and we can put in the mass, the acceleration, and 9.81 to find out what the net, not net, what the thrust force needs to be. I'm going to add this to both sides first. And I'm going to make a point that I think I've made with you as a class a couple of times this semester, and I've made it maybe 20 times with my physics 30s. We're done the physics. This is the physics. Putting the numbers in is math. Okay? And if this were a written response, I would be more interested in your ability to do this and explain what's going on rather than what you get for an answer. Although the answer is important, right? I'm writing it this way. Let's put in the information here. Let's see, 250, that's 0.25 kilograms. Times the acceleration of 32.4. Was it 32.4? Thank you. Plus 0.25 kilograms times 9.81. And I want us to calculate, just humor me here, I want us to calculate both of those. I want to calculate this, and I want to calculate this. I can do this one in my head. I can't do the other one in my head. You get 8.1 newtons here. I think 32.4 times 0.25. It's a quarter of 32.4. And then the other one, 0.25 times 9.81 gives you 2.4525. This is our answer. So our answer is the sum of those two forces. Just want to make sure I wrote that down correctly, which will give us 10.55 newtons. You get the right answer, the same answer? Okay. Now I just want to show you something. If I would have taken and ignored gravity, I would have got 8.1 newtons. That 8.1 newtons is not going to accelerate the rocket up at 32.4 because it's going to lose the force of gravity. So you have to apply that much extra in order to get a net upward force that would produce that acceleration. Take a look at the next one. A skydiver is jumping out of an airplane. During the first few seconds, the parachute is unopened. And let's talk about reality here. How many times have we seen problems neglecting friction? Right? Friction can be neglected in situations like this, but friction cannot be neglected with air when you're moving fast. If you don't believe that the force of friction between you and air is large, don't do this, please. But imagine driving down the highway at 100 kilometers per hour, unrolling your window, and sticking your hand out suddenly. Probably pull a muscle, minimum. The force of friction gets very large when objects are moving very fast through the air. Right? And has anybody ever skydived? you can imagine there's air coming up at you, pushing you, right? So during that section of the fall, here's the skydiver. Okay, that's how creative I feel today. There's the skydiver. There's a force of friction of 250 newtons. Well, they're moving down. So that force of friction is upward. Now, when you jump out of a plane, the force of friction is up. Does that mean the person starts rising? No, because there is also a force due to gravity. And by the way, I'll save that. There's something I want to talk about, the force of gravity and the force of friction here. So during one portion of the jump, the force of friction is 250 newtons, and the acceleration of the skydiver is almost 6 meters per second squared down. That downward acceleration tells me the force of gravity is more than the upward force of friction. Well, MA, F net, in this case will be the force of gravity minus the force of friction. Magnitudes. Magnitudes. So I'm including the direction when I say minus. This will be MA. Did it again. This will be MA equals mg minus the force of friction, and we can put the numbers in. Oh, we want to find the mass. That's interesting. Okay. So let's put all the numbers in. We have mass times 5.96 equals mass times 9.81 minus the 250. So, look, if this were a math class, and I gave you 5.96x equals 9.81x minus 250, you can solve that. It's what I would call a very basic, put that away. It's what I would call a very basic linear equation, where you collect all of the terms that have your unknown on one side and all of your numbers on the other. Unfortunately, I haven't taught any of you math, I don't think. Oh, I have, yeah, a couple. You want to move all of your x terms to one side. This is my advice. Since you have more x's on the right, move the x's to the right. So I'm going to take 9.81x and subtract 5.96x. This negative 250 is going to go to the other side. So what I'm really going to have here is 9.81m minus 5.96m equals 250. $9.81 minus $5.96 is found by subtracting those numbers. So I'm going to take 9.81 minus 5.96. I want to say 4.85 when I subtract those numbers. 3.85? Okay. So I get 250 equals 3.85 m. I can divide both sides by 3.85 and get the mass. So about 65 kilograms. Any questions with that one? All right, we have one more bulky question to go. I believe it's an ABC situation. 3,200 kilogram elevator is in a building. What is the tension in the cable? Okay. Well, the tension in the cable is the applied upward force. If the acceleration of the elevator is up at 2.5, I'm just going to throw something out here and see how many of you it sticks to. To how many of you does that make sense in this particular question? Okay. Let's just walk away from this for a second. What if the elevator were accelerating down at 3.5? To how many of you does this make sense? You starting to get my drift here? That when it's accelerating up, and again, I don't feel real creative, although I can draw a box, that's easy. There's my elevator. Here's the cable that, supports it. If it's accelerating up, we have a force of gravity. You cannot hide from gravity on the surface of the Earth. It's there. But if it's accelerating up, then the upward force has to be greater than the force of gravity, which is why I said F applied minus the force of gravity. Because the net force means add them together. How do you add those two forces? Take the bigger minus the smaller. And what I'd like to do is set up all three of these. There is an ABC, isn't there? Okay. Set up all three of these. So here what you would have would be your cable. You've got your elevator. You have the force of gravity, which is the same as it was before, but now you have an upward force which is less because the elevator has to accelerate down. This may be a little counterintuitive, which means it might seem weird. But the reason it has to accelerate down is that force of gravity has to be more than the applied force upwards. And by the way, I've actually had a student say, well, why do we even need an applied force upwards? The answer is because otherwise you'd be in free fall. Be accelerating downward at 9.81. The cable will have broken. That's not what we want, right? Let's take a look at C. What do those forces look like if the elevator is accelerating up? If the elevator is accelerating up, there's a force of gravity, but it's accelerating up at a constant speed. What will the applied force upward be? Any ideas? Declan, do you have an idea? Would be equal. And this is a little counterintuitive because some people want to say it would be bigger because you're moving up. If it was bigger, you'd be accelerating up. If it's smaller, you'd be accelerating down. So Declan's answer is perfect. It's equal to the force of gravity. In magnitude, right? So here we have an upward applied force. This is Fg downward. This is F applied upward. And we don't even go with F net here. I guess you could say F net is 0, but I would just say in this case the applied force upward equals the force of gravity downward in magnitude. I really don't mean to minimize the rest of our work here, but that's the physics. This is the physics. This is the physics. Just to go one step further, I guess we can write MA equals the applied force minus mg. So if you want to calculate the applied force, which is the tension in the cable, you're going to take MA plus mg. I'll give you a minute to calculate that. However, I will throw something else your way. If you look up here just for a minute, I can factor the mass out and be left with A plus G. And that makes sense because you have to apply more force. You're going to add the acceleration plus 9.81 and multiply by the mass. But can you do me a favor and calculate the answer to this question? You can use either ma plus mg, or you can use m times a plus g. It won't matter. So 3,200 times 2.5 plus 3,200 times 9.81 gives me 39,392 newtons. Do you get the same number? Okay, good. If it were accelerating down, then this is the formula. Now, let me write ma and mg in here. Ma is the net force. This is mg minus F applied. On the heels of what I just talked about a few minutes ago, when I'm rearranging for something, if it's negative in the formula, I move it to the other side to make it positive. So I'm going to kick the F applied to the left side by adding it to both sides. And that means I have to take mg and subtract ma, which kind of makes sense. I don't know, it won't to everybody. But the applied force is going to be less because gravity is helping out. That's maybe a way to think of it. Again, if you like, you could do this. And again, don't confuse G, which is 9.81, with A, which in this question is 3.5. And again, you're not going to put negative 3.5 in there. The negative is in there because we're subtracting. Okay? 30,272 is what I get. No. Missed the zero there. 21,152. Three strikes and I'm out. I can stay, I think. 20,192. So the tension in the cable here would be 20,192 newtons. Here, we just have to calculate the force of gravity, and that's the answer. So what is the force of gravity? It's 3,200 times 9.81. $31,392 newtons is the tension in the cable. We're done. That's the last example, yes? Yeah. Let me throw just one last thing your way. Rather than doing this, I'm going to show you something else, and I'm sure many of you will realize right away it's the same thing. Would you agree that if you have an upward force and a downward force, the net force is found by subtracting them? So that means that the net force equals the applied force upward minus the force due to gravity. Yeah? What's the acceleration in the third question here? No. That's the 9.81 is G. I'm asking what is the actual acceleration of the elevator, Aoki? It's 0. Which means when you put 0 in for A, you're going to get 0 for a net force, which is obvious because the force is balanced. But what you're going to be left with is 0 equals the applied force minus the force due to gravity, but that's the same thing as saying that. Those two forces have to be equal. The weird thing about this, though, is I could have subtracted these in the opposite order because there isn't really a bigger one. It's just the difference between the two giving you 0. So some people might prefer to think of it that way. Again, in all of our work for all of these, when we build this equation, you build it from a free body diagram. If I see you doing work and you're not getting the right answer and you don't have a free body diagram showing the upward and downward forces, that will be the problem, right? That's what you have to try to remember to do. And in all of these, when we build the formula, the pluses and minuses are built in based on how we subtract the forces. We don't put negatives in for the actual forces. So for applications of Newton's second law of motion, including what we will be doing tomorrow and Friday and Monday, because there's lots of other types of situations, you need to draw a free body diagram, use the free body diagram to find an expression for the net force, set that expression equal to MA, and solve the problem. Okay? So there's a bit of thinking that has to go on here. It's not just grab a formula. If you want, you can take a picture of that or you can write it down. I'll leave it up there for a little while. Get to work on those problems. 1 to 5 at a minimum. I've also got a couple of practice problems from your textbook if you like.